Hello, everyone. Welcome back for those who were already with us, and welcome to those who are joining us for this second hour of this webinar on paratransit electrification. Thank you very much for joining us today. This is the second session of a series of 3 webinars all happening today. And these webinars will explore how cities in Africa can turn one of their most widely used transport modes, paratransit, into a cleaner, safer, and more sustainable system. First of all, let me introduce myself. I am Joanne Collet, Mobilize Your City Partnership Global Secretariat based in Brussels, and I am a sustainable mobility expert. Before we start our session, a few reminders are on the next slide, please. So please make sure that your microphones and cameras are turned off. It should be automatic. We would also like to inform you that this webinar is being recorded, but if you keep your camera off, you will not appear in the recording. Your questions are welcome. We will be happy to address them, so please feel free to write them in the chat. There will be time to address them at the end of the session. And finally, we would greatly appreciate it if you could take a few minutes to complete our feedback questionnaire at the end of the session. Next slide, please. To present this webinar series. So this webinar series is the result of a collaboration between partners who are all working on paratransit and electrification. These partners are TUMI, Changing Transport, C40 Cities, GIZ, and Mobilize Your City. Each of these organizations works on this topic from different angles, and we felt it would be highly valuable to come together and share knowledge and experiences. So we're very excited about this webinar. And before we dive into our topic, a bit of context first. So paratransit is one of the most widely used forms of public transport across African cities, but it also contributes significantly to air pollution and greenhouse gas emissions. And this is largely due to use of older, often second-hand vehicles and the high mileage associated with daily operations. Decarbonizing the sector presents then a major opportunity. It can help modernize fleets by replacing outdated and unsafe vehicles, improve service quality, reduce both local air pollution and emissions, and potentially support a shift toward higher capacity and more efficient vehicles. Next slide, please. This webinar series is organized around 3 parts, each from 1 hour. In the past hour, we talked about regional lessons on enabling policy and regulatory framework, and we draw on particular. We draw them from insights gained through the Nairobi study tour. Second, so right now we will introduce practical tools for policymakers, operators, and investors to help advance paratransit electrification in their own contexts. And for that, we will look at the Mobilize Net Zero tool. And third, we will explore how to capacitate city, regional, and national government on GHG emissions calculation on the paratransit sector in aid of climate action plans and NDCs. So this is the second hour. Welcome. We can move to the next slide. And we have until 11:55. So we hope we'll find it interesting. And please feel free to stay for the next hour if you have time and if you feel like it. Now let's get started. And I'm leaving the floor to Abdul to start the session. You're muted, Abdul.
Sorry.
Yes.
Welcome to this session, and my name is Abdul Jalil Zakaria, and I currently work as a sustainable mobility consultant for GIZ Mobilize Net Zero project. Next slide. So the Mobilize Net Zero project is a global program that seeks to help governments to amplify their commitment towards decarbonizing the transport sector. Next slide. And in this particular program, there's a component that's currently being implemented in Rwanda, And as part of that component, we are looking into the topic. One of the activities has to do with the topic of paratransit, and specifically looking at how best we can decarbonize the paratransit sector within Africa. And quickly, I would want to show you some of the products and activities we've done within the topic of decarbonizing the paratransit sector. So one of it has to do with we were able to develop an EV transition toolkit for minibus operators, which is the reason why we are here for this particular webinar, where we would be demonstrating how best as policy makers and operators, we can be able to use these particular toolkits to make evidence-based decisions towards electrifying our minibuses or paratransit fleet. And you can scan this code to access the toolkit, which has been published in the Changing Transport website. Next slide. We also have a discussion paper on minibus electrification in Africa, and in this particular paper, we explored how ICE-powered minibuses can be electrified across Africa. So how do we replace these ICE minibuses to electric minibuses? So in this particular paper, you would find out the recommendations that were being proposed. And you can also click on the link to access this particular publication on the Changing Transport website. Next slide. We also have the National Roadmap for Paratransit Reform, and this was recently published, and basically it provides how African cities can be able to reform the paratransit sector by making sure it's inclusive and in a more structured approach. Next slide. And finally, you can visit the Changing Transport Knowledge Portal to have access to all these publications on paratransit decarbonization that I've spoken about, in addition to others that currently other countries have been working on. And just to let you know that right after this, but this is the introduction section. My colleagues would be presented, telling us about introducing themselves, and then we dive right into the toolkit demonstration. And afterwards, you would have access to ask any questions you have regarding this particular toolkit. Over to you, Justin. Next slide.
Good morning, everybody. It's lovely to see lots of familiar faces and names in the list, and also some new ones. So lovely to see you all or meet you all. So my name is Justin Coetzee. I am the founder and CEO of a company called Go Metro, and we have an advisory arm called Better Rides, which is our advisory on transport service division. Next slide, please. So just a brief introduction. We essentially help cities, operators, transport planners to unlock the value of data and electrification so that they can implement greener mobility strategies successfully. Next slide. Data is the key of everything we do. So we have extensive transport data and survey experience, operational optimization expertise, as well as a tool called EV Fit, which is a telematics-based EV transition planning tool. And we use a lot of these tools and toolkits to build a ready-to-go toolkit that any city can use or any operator can use to start moving towards electrification for their paratransit operations. Next slide. So our transport data products and services are all mostly digital, online, and new technologies that unlock different ways to collect data other than a paper and clipboard. If you want to know more about that, then please do drop me a mail. Next slide. And our operational optimization, often we find that the cleanest trip is the one you don't do, and there's significant amounts of operational optimization opportunities. So there was a question in the previous session about scheduling. we find that scheduling is low-hanging fruit when it comes to reducing emissions. So you can always schedule and optimize before you electrify, and those are already reduced emissions if you're reducing the running kilometers of a fleet. Next slide. And then finally, EV-Fit is an online tool and that brings all the different aspects of electrification together, particularly in an ad hoc setting like a paratransit operation, where kilometers differ and the distances vary day to day. And it's a very challenging operation to electrify. EV-Fit uses telematics data to help inform investment decisions. Next slide. And when you put that all together, you've got data sources, you've got operational optimization, and then you've got the transition to EV. And that's the full life cycle that we offer to cities, authorities, operators, OEMs, private equity investors, all looking to help Africa electrify its paratransit and public transport sectors. Next slide. Just a showcase of just some of the countries and cities that we operate in. So it's predominantly a global south practice, but we are also using these technologies developed in the global south to inform and help electrification in territories such as Canada, the UK, Australia, and the US. Next slide. We have supported and helped bring the first electric minibus to South Africa. Roadworthy, road legal ability to operate an electric minibus. So we don't only write reports, we also get our hands dirty and greasy by working on vehicles and implementations as well. Next slide. We also supported the Red Cross, Ethiopian Red Cross, in sourcing and finding a replacement to the diesel guzzling Land Cruiser, and looking at how we can bring robust ambulances that are electric. So that was quite an interesting study to figure out how to electrify the Red Cross fleet for Ethiopia. Next slide. And lastly, we've also then piloted the public-private partnership for taking a public facility, a terminal in Stellenbosch, and looking how to use that rank to be an electric hub. So starting with a hub that then attracts operators to electrify and removing the infrastructure challenge. So these are just a few of the examples that we've used, and then we've used these lessons in developing the toolkit, which I think Duan will now present. So thank you. I think that's our intro done, and over to Duan.
Awesome, thanks, Justin. Hello, everyone. My name is Duan Steyn. I'm chartered economist for Metro. One can hear me fine. Am I allowed to share my screen?
Yes, please.
Hi, Duan. Thank you. You should normally be able to share your screen, and I think your sound is a little low, just for information.
Let me just see what's going on. Can everyone see my screen? Can you hear me correctly?
Your mic is low, Duan.
Strange. Is this better?
It's still very low. We can see your screen though. It's not full screen, but we can see it. But I think we have a bit of a sound issue.
Let me just try again sharing. I think there's something wrong. Is this better?
Yes.
Is this better? Can you guys hear me?
The sound is still low, unfortunately. If there's no other solution, we'll just have to pay extra attention.
Yeah, my mic is up fully, so I'm not sure why the sound's not going through.
Can you move close as possible to your mic, Duan?
Yeah, I'm basically screaming, but it's fine if you guys can hear me. It's cool.
Yeah, that's better. I think the closer you are to the mic, the better.
Yeah, let me try and be as close as possible. Cool. So yeah, hopefully you guys can hear me fine. So yeah, just a bit of background on this project. We try to, through interviews and some research and with our experience, create a pathfinder, as we'll explain just now, and a toolkit. The toolkit actually is part of a series of tools to make the decision to move from ICE vehicles to EVs as simple and easy as possible, to look at different scenarios, to look at different aspects, and to see whether there is an EV business case for various stakeholders. So you'll see here with the Pathfinder, we designed this Pathfinder for different stakeholders to, as a beginning point, if they're unsure or unaware of where to start and what questions to ask if you want to transition from ICE to EV vehicles. So unfortunately there's about 7 toolkits that we developed, but for the time constraint we have for today, 30 minutes, I will take you through the operator aspect and the operator Pathfinder and the toolkits applicable to the operator. So for example, if I'm an operator and I don't know where to start, I can always ask myself the question regarding my routes and my vehicles. Do you know if your route is suitable for EVs? What's the distances I travel? What's the dwell times? What's the terrain look like? If I don't know this, we developed a tool called the Model A, which is the technical feasibility. This is a tool that captures the route profiling, the charging needs, and also the workshop readiness. And then the second aspect of the operator Pathfinder is the financial viability aspect, which is the TCO model. So these are the two main tools for the operator that we'll be looking at for today. And then the outputs of these two tools will serve as the input for the risk and readiness toolkit that highlights the risk profile of this specific operator with the inputs that they gave. So I hope that makes sense. So I will then follow the route and I will now demonstrate the Module A, which is the technical feasibility tool. Cool. As you'll see here, the tool has a landing page. So this is kind of like a guidance page for the operators to see how the tool works. It gives a nice overview of what the tool is. It gives what the 3 core questions is that this tool aims to answer, which is, can my current operations transition to EVs? Is the route feasible? Is my vehicle feasible? Is the charging infrastructure feasible? And also, do I have a workshop that's technically ready to maintain the EVs safely? It also gives how to use the tool. Also gives the cell colors and navigation, what each cell means, what the color means, but I will demonstrate that as we go. We also include the methodology and the evidence base and also the limitations of this tool. So this is just to give as much as possible, as much background as possible for anyone that's using this tool. So if we go into the tool itself, you'll see it's very simple, it's an input-output model. The blue cells here will representing the inputs of this tool, and the yellow cells is the output. As I mentioned, the first part will be the route profiling to see if the specific route is feasible for each to transition to EVs. The second part will be the vehicle suitability. We then go on to the grid and charging feasibility, and then lastly, the workshop readiness. So very simple, we begin, we just input aspects like the route ID, it can be anything. We go into the distance, and that is the one-way distance from the start to the end of the route. How many trips a day this route is operated on. Dwell window, so we've got options here, overnight, midday, or both. So this is when the vehicle is or vehicles is not operating when it's idle. The terrain, also very simple, flat, mixed, or hilly terrain. This is quite important because we've added efficiency factors to this. So you'll see if it's a flat road, we have a factor of 1. If it's mixed, a factor of 1.1, and if it's heli, a factor of 1.25. The same with the passenger load. The option is how full the vehicle is on average, low, medium, high. Next one will be the overnight idle. How many hours do we have overnight to potentially charge this vehicle? Then we have the daily distance override. So this is basically if the operator doesn't know what their route distances are, what their amount of trips are per day, they can add a single kilometer distance here, and this will serve as the override and modeled kilometers for this model. We also have here the highest and lowest expected operating temperature. So basically the optimum operating temperature of EVs is 21.5 degrees Celsius, and any deviation from that affects the efficiency of the vehicle, and that is why we have these inputs. You'll see here we have the derived kilometers here, because we have an override vehicle distance here. It takes the derived kilometers, but if we take it away, it calculates the route distance for the trips per day. Next, we go into the battery efficiency or the vehicle efficiency. This is the advertised battery efficiency that you'll typically get from the OEM or advertisements. So that is the default setting will be the battery to wheel efficiency. We did add another option here, which is the wall to wheel option, which adds the charging losses if it's not included already. So that's just an alternative option we have to make this a bit more accurate if that is the case. But the default most of the time will be the battery to wheel option here. So with all these inputs, we can then determine the adjusted efficiency based on the operating temperatures, the loads, the terrain. Then we have the adjusted efficiency and then the daily energy needs per vehicle. So how much energy do we need to operate one EV vehicle on this route? So now we have the route profile, a simple route profile for this route. Next will be the vehicle suitability, which will be the battery size, as you see here. And again, we have two options here. The installed battery size, this is the gross size that's advertised by the OEMs usually. And then we've got the usable on board. So if it's advertised as usable on board, then the manufacturer buffer is already removed. But the default again will be the installed capacity here. With all these inputs, we then have an effective range of the vehicle on this route. And you'll see here that the green cell is a route and vehicle feasibility decision, which is a conditional go. This is because the effective range you'll see here that it calculated, and the distance is more than the distance of the route. So we'll see here that based on these inputs, we can see that the vehicle that we chose and the route that we chose is feasible at this stage. just to show the workings of the model, I will now change the distance. Let's say the distance is now 300. You'll see that the decision goes to maybe. So you'll see that the effective range of the vehicle is less than the daily distance operated. So this means we need a midday top up. But because we chose midday as an option, it gives a maybe the verdict, because now we know we have a chance to do a top up charge during the day, during idle hours. But if we only charge overnight, then this would be a no-go, because then we don't have any opportunity to charge midday. I'm just going to change this back. Cool. So now we know the vehicle and the route is feasible. Now we're going to have to look at the grid and charging feasibility. To keep this simple, we will just use one vehicle in this explanation. The charger, that's the size of the charger, is 60 kilowatts, and then the overnight hours available is 6 hours. The midday hours we chose here as 4 midday dwell hours. And then the last input that we need for this model is in the total grid capacity at the depot. What's the total capacity at the depot? And then what's the current peak at night? So this is what's the demand for charging overnight. So basically this is the capacity for the depot, and this is the demand excluding EVs at this current point. This is, we do the same then for the midday. And this is important because we need to calculate the headroom, the available power for EVs during the night and the day. So you'll see here that the headroom is calculated by subtracting the total grid capacity by the current peak for the nighttime charging, and the same for the midday charging. Now we've input all our variables. The model then automatically calculates the rest. We can see that it automatically calculates the maximum achievable overnight charge capacity. Same with the midday. And then also the total daily energy that's needed. Based on our inputs, we can see here that we have a per vehicle deficit in kilometers of 47 kilometers. So we need a we need to top up with 47 kilometers, which is based on our efficiency, roughly 17 kilowatt hours to complete this route. You'll see that we only need 17 kilowatt hours, but our max charging achievable during the midday is 183. So this is then a feasible solution. We can top up midday. The grid is sufficient midday, the grid is sufficient at night, and our decision will be a conditional go. Just to again showcase the model, let's just change the dwell hours to only 1 hour, and let's change the distance to something very high, like 700. And you'll see the decision for the grid will be no-go, because we need a top-up of 161, and our max charging achievable during the midday, because we've got a lower window, is only 45. So that's the workings of the grid and charging feasibility aspect. The last aspect is the workshop readiness. This is very simple, not as technical as the charging and the vehicle feasibility. This is just a checklist to see whether the workshop has been thinking about workshop readiness for EVs. And this is a very simple yes, partial, or no choices. And this then calculates the decision based on that. For the essence of time, I'm just going to move on. So we have our decisions now. This is then displayed in a dashboard. Gives the 3 main decisions for this technical feasibility. It gives a maybe, a no-go, and a no-go output. It also explains exactly what each means. And then we've also added some action points and what needs to be done to actually improve the output of the model. For some user friendliness, we've also added an info and definitions tab. You'll see it follows the model exactly. It gives the items. It gives what it means in plain language, what cells it is in, what you need to do, where to get the info, and how the model actually uses this info. We've also added input prioritization, what inputs within each aspect is crucial. So you'll see some of it is crucial and some of it is not crucial, where we can use proxy numbers and the model will still be working. We've also added a actions library, so you can go look at what your decision is, what its decision means, and what levers you can do to improve the outcome of this model. And then lastly, we've also added a vehicle spec. Based on some research, we've added some vehicle specs of existing EVs that you can use to plug into the model if you have no idea where to start. So yeah, that is the technical feasibility model. As I mentioned, this output will serve as input for the risk analysis model. But for now, let me take you through the Pathfinder. So we completed the Model A technical feasibility. We now need to move to the Model B, which is the TCO model, which I will showcase now.
While Duan's bringing that up, it's important to note what we're aiming to do with this tool is that with a tool that you know how to use, spreadsheets, you're able to get 90% of the knowledge and information you need to electrify your fleet. So just by following the process, the A, the B, the C, you're able to assess your own fleet, and demystifies the electrification of paratransit fleets.
Cool, thanks, Justin. Cool, so moving on to module B, which is the TCO, total cost of ownership model. So for those who don't know, TCO models, the aim of it is to compare the total cost of ownership, which includes the operating costs and the capital costs of one technology, which is the ICE vehicle, compares it over time to another technology, which is the EV, and then compares what is more expensive and where the potential, if any, break-even point is. So again, the landing page here just gives a nice overview of what the TCO model is and why we built it. A high-level overview of how to use the tool. Again, the cell colors, what it means, the methodology, and there's some important limitations. Next tab will be the basic inputs. Here we will input aspects that's for both diesel and the electric technology to compare the two. Because remember, we need to compare the two to see what the TCO is. So again, very simple. What is the vehicle, or in this case, the minibus price for diesel versus electric? In this case, we use dollars or American dollars, but this can be adjusted to any currency. We have the infrastructure cost here. You'll see the yellow cells, which is the automatic calculated cells, pulls through. So this pulls through from an independent infrastructure cost tab, which we will go through now. Here we see that we already inputted that we need 100 vehicles. Then this is an optional input we had. We brought in to compare apples to apples, for one technology to another technology. For EV, you'll probably need depots, infrastructure costs. So if you want to compare true cost of one technology to the true cost of another, you need to see what's the construction cost of, for example, a gas station. But this is optional. It's just an option we gave just to demonstrate that this tool can be flexible. Cool. So the rest of the inputs are quite easy and very straightforward. For the vehicle, what battery size you're looking at, what charges you're looking at, and this then automatically calculates a few things. For example, it calculates the time to charge one minibus, and then if we input the available hour to charge at night, this then automatically calculates the amount of minibuses you can charge per charger and the number of chargers you need, and then the cost of the chargers per charger. You get the number of chargers per depot as it's an input value. So you'll see here, because we calculated that we need 9 chargers, we want 6 at a depot, we will need 2 depots. But if we change this to 9, then we only need 1 depot. I'll just keep that at 6 for now. Included the cost of a charging depot, which is basically the civil works and electrical, as you see there, inputs there. And then we included a lease per month. If, for example, if you have a case where you need to lease land for depots for EV charging, it can be inserted here, but it's also an optional input, so it's not needed to put it in if that's not applicable. So basically, this then calculates the total infrastructure costs for the 2 technologies, and that's the automatic calculation you'll see here. Let's put in there. The rest of the inputs is quite fairly straightforward. We'll see insurance costs for the minibuses, insurance costs for the chargers as a percentage of the asset value. The energy costs for diesel will be the diesel price per litre, and then the electric energy cost will be the cost per kilowatt hour. Maintenance costs per kilometer we need to input for diesel, and then we automatically assume a 60% of that maintenance cost for EVs. We already said we inputted 100 minibuses. We can input the life cycle we expect from each. The kilometers per year is automatically calculated based on our operational profile, which you see here. And then we actually need to insert the efficiency per kilometer or kilowatt. So based on that, we can actually automatically calculate the capex for each and also the opex for each. And then also, apologies, we need to calculate the battery replacement costs. So we insert the battery capacity, the prices per kilowatt hour, we estimated as $200 per kilowatt hour. And then we assume a 60% reduction in battery capacity over 8 years. That is quite conservative, so yeah, that could change. And then we calculate the battery replacement cost. So basically the amount of battery that you used over the 8 years as a real value. What we also added here is incentives, if there's potential any incentives for EVs. To keep it simple, we added only vehicle capital incentive, a infrastructure capital incentive, and also an incentive on the electricity price. So for this demonstration and this scenario, we'll only insert, for example, the vehicle capital incentive, and we'll look at the outcome. So now that we have all our inputs, we just need to add a few more specific ICE and specific electric inputs. This is done in this tab here. This is the TCO ICE tab. You'll see most of it is already calculated automatically. And then we just need to add a few assumptions here. The equity percentage, the down payment, the interest rates for minibuses, the payback period is 10. For this model, 10 is the maximum here as a conservative number. Insurance rate already automatically calculated. The infrastructure payback period, and the maintenance percentage per year. And then from the OPEX side, most things are calculated automatically, and we just need to add variation in diesel prices and also the inflation rate. Once that is inserted, the TCO engine does all the heavy lifting, and I'll show you the outcome in just a few minutes. So next we do this precisely the same for specific EV inputs. You'll see again equity down payment. We've added battery replacement cost, obviously. Insurance, inflation rates, all those inputs, and then specifically to OPEX, we'll do the annual variation in electricity prices as a percentage, also as in the annual inflation rate. So once we have all these inputs, now we can look at the outputs and compare the two technologies. The TCO does all the heavy lifting, and the cost comparison will look something like this. You'll see a nice summarized table and it compares the total cost of ownership of diesel versus the electric. It divides it in capital costs for the vehicle itself, for the infrastructure, also for the OPEX will be divided into energy costs and maintenance costs. The depot lease, if applicable, is then also added. And then we have the total cost of ownership. This is in $1 million. As you see in our example here, the TC over 10 years, we'll see in this example that the total cost of owning this fleet of ICE vehicles over 10 years is more than the turbo electric counterpart. specifically to see the difference between OPEX and CAPEX, we'll see here that the operational cost of owning the diesel fleet much higher than that of the electric aspect of owning the fleet. The opposite can be said of the capital expenditure, the diesel case, less in capital initial investment, whereas the electric counterpart more expensive in that regard. But now the question is, can the operational savings for EV catch up to the high capital cost of the EV? And that's where the next tab comes in. This is the break-even point. So this is where the cumulative comparison between the two technologies, so cumulative costs over 10 years, we'll see here, if you look at year 0, this is the initial investment. We'll see that the electric minibus taxi fleet much higher than the ICE. But as time goes on, as the vehicles start operating, you'll see that the ICE vehicle catches up, the electric vehicle catches up to the ICE vehicle, and roughly around year 4 or year 5 in this scenario is the break-even point, where actually owning the electric fleet becomes less expensive than owning the diesel fleet. So yeah, that is the total cost of ownership model. I see you've got about 3 or 4 minutes left. Let me show you how this plugs into, because I mentioned, you remember I mentioned it plugs into a risk analysis model. So let me show you that one. Again, I won't go through the guide. Just gives an overview of what it is and what it means to do. So we'll see here is the risk assessment. Here we'll have all our modules. We went through the technical and the TCO model now, but we still need to do this, but due to time, we're going to skip these and we'll just focus on what we did now. So that, as I mentioned, the outcome will be the input for this one. You'll see I already repopulated this one. So for the route and vehicle feasibility, we see we have a maybe outcome. This gives a risk statement explaining what the shortfall is and what risks there are. What is the trigger condition? For example, the effective range is less than the vehicle effective range is less than what the route distance is. So that is why we have a maybe outcome. We'll see here the mitigation aspects, and then the score, the risk score. For the grid sufficiency and workshop readiness, we have no-goes in this example we used. And this also then gives the risk statement, what the trigger condition is. And this we'll highlight, we'll see, oh, okay, this is a bit more of a risk for those two inputs. Then lastly, the workshop readiness, or the TCO, we should have conditional go. We'll see, okay, this is very cool, it's a conditional go. But from the financial aspect, we see that the cost of owning an EV is is less than owning the ICE vehicles over 10 years. So this is a conditional go verdict and less of the risk. So yeah, that is the toolkits demonstrations for today. As I mentioned, there's other models as well, but unfortunately we won't have time to go through everything. I think we went quite quickly through these as well. So yeah, thank you for listening, and I think it's now time to take some questions if there are.
Thank you very much, John, for the demo on the various toolkits we have. And as he said, we have other toolkits. All have been published, and if you want to play around it, you can please visit the Changing Transport website, and you would have access to all the toolkits. Thank you all for paying attention. And now to the question and answer session. We already have a few questions coming up. And the first one is from Andres. He's asking, that, okay, the first one is for me. You want to know about the current biggest barriers to electrification. I would say currently one of the biggest barriers to electrifying mini buses has to do with the current upfront cost, even though over time it becomes more profitable, but still the initial capital requirement is something that operators keep complaining about. And so therefore there's a need for innovative financing mechanisms to help these operators to be able to easily access finance and be able to procure some of these electric mini buses. And you realize that the nature of the informal sector is such that it's mainly made of individuals and small fleet owners. So trying as much as possible to consolidate the sector such that they are able to come together and mobilize, go as groups or as cooperatives to access this financing are some ways to overcome this particular barrier. And when you read the paper, the discussion paper, you realize that we have a lot of propositions that were being made on how, about 8 propositions. And once you go through it, you understand what exactly needs to be done in order to ensure that we are able to transition successfully, how we can transition successfully the minibus sector. Thank you. So the second question is for Justin. So you told us you are working on a pre-feasibility study to electrify Ethiopian Red Cross cars, and these cars work most of the time in rural areas where it's hard to get electricity. So do you think it will be feasible without access to electricity, and how will they overcome range anxiety and other challenges? Justin?
Thanks. Yes. It all starts with data, the telematics data, the route data. Because if you can provide a charge point at one location, even if it is in a rural area, and that vehicle can get back to that charge point within an acceptable range that the vehicle allows, then you can support a satellite hub that can run. Electrification in major rural areas is a huge challenge, and shouldn't be undertaken lightly. The biggest barrier for that project with the Red Cross ambulances was the availability of the appropriate model. And I think that's what we're still seeing, is that it's very difficult to source and find appropriate model choice, battery size, and range for African applications. Electric vehicles generally come for urban applications, low mileage, steady operations, and there is almost a extra layer of automotive engineering to Africanize the vehicle with additional range, additional suspension, additional height, additional operating conditions for the operating conditions we find in African operating areas. And rural charging and rural operations is particularly challenging. We are working on a mobile battery that's 233 kilowatt hours that can charge from solar or charge from a source and then be wheeled somewhere else. So we are working on a mobile charging unit that can be put on a trailer, charged at a hub, and then gone and put in a village or put somewhere further away. So yeah, I think that electrifying shuttle routes, electrifying feeder services that feed a suburb to a hub or something like that, that's very doable. But going more and more, the more rural you go and the more distance you go, the technology still has significant limitations which need to be respected.
The next question is from Rolex. He's asking, in administering the technical feasibility model, what are examples of potential action plans for EV transition for the no-go result? Is it setting up workshops for repair, charging infrastructure, etc.?
Cool. Yeah, thanks for the question. So for the technical feasibility tool, we had to make a decision between how complex something is and how easy to use it is. So for the workshop part of the question, we actually only made like a checklist to see what the thinking is. We haven't included any workshop recommendations. Sorry, yeah, talking so long. Recommendations for actually the outcome. And then what's the other question?
Okay.
Examples, potential action plans for EV transport for no-go result. Yeah, so the action plans are included in that final module, the risk model. So the inputs, as I mentioned, the outputs of the technical aspect guides the inputs for the risk model. So the inputs then, if it's a no-go, it will give some advice on how to improve the result. That's why I said that it's interlinked. The technical feasibility model and the risk model is interlinked. So it does give that answer.
And if I can just add to that, the number one intervention that's most likely to improve a technical feasibility model is placing chargers at every place where the vehicles turn around, park, dwell, or hang out. So wherever we can put chargers, you'll extend the range of those vehicles. So the number one implementation is not one single hub, but a hub with a bunch of satellites that can offer charging at the end of a route.
Thank you. The next question was on the TCO model. He was asking whether residual values were taken into account, and I can see a response from Justin. Would you like to throw more light on that, or we move to the next question?
Yeah, so just one comment on it, which is that we're seeing batteries last a lot longer in practice. So we've got some buses in London which are 12 years old, 13 years old now this year, and they've still got the original battery, and their degradation is much lower than we all thought. We thought it'd be 2%, 3% a year, which is where this 8-year cycle comes from, so that you've got at least 80% life. But we're seeing a long life on these batteries, and that's 10 years ago technology. So you can imagine the batteries coming out today are even better. So I think our message to the industry is don't worry too much about battery residual values and battery performance. The battery as a technology is massively outperforming the 8-year lifespan that we all expected.
Thank you. And to the last question, for the TCO2, what is the assumption for the battery lifespan for EVs, as this probably comes with replacement cost after several years of charging?
Yeah, I think Justin actually also touched on it now. The assumption we made for the TCO was 8 years, but as he mentioned, that is a very conservative number, and we're actually seeing that battery lifetime actually is much more than that. But yeah, we took 8 years for a conservative number.
Thank you. I can't see any more questions. And we have 2 minutes left to the end of this session. Any questions? So as I said initially, so try as much as possible. Let's go play around with the tools. And if you have any feedback, you can, or need any assistance on how to use it, you can always reach out. We have a question from Willie. I hear you, Justin, but old Toyotas last much longer than modern ones. Technological advances chase efficiencies and not longevity. Any reactions?
Yeah, so two things. I was thinking about this now. One is what we see in practice is operators moving these vehicles that maybe have a reduction in range. So battery degradation is a reduction in range. That's all it is. The motor still works, the battery still works, the system still works. It's only a reduction in range. So what's likely to happen is that I'll get a bill to replace the battery to get another 20% range, or I'll put this on a shorter route or a school route or a contract route, and I'll shuffle the vehicle around or dispose of it. So I do think that the market will accept this much more readily than the battery replacement theory which we give it. And you're absolutely correct, Gerald, Gerard. The chassis and the rusting of the chassis and the mechanical breakdowns are more likely to affect the vehicle, and that's why mechanical soundness aligned to African operating conditions is probably a very important engineering requirement. And probably the biggest risk for EVs entering the market is too thin metal, too little suspension, too short brakes. It's the mechanical nature of the operations being insufficient for African operating conditions that pose more of a risk than the battery and the motor, in our professional opinion.
Thank you. We've run out of time. Yes, I would reshare the link in the chat. Thank you very much, Justin. Thank you, Duan, for the amazing presentation. It was a pleasure being the moderator for this session. Over to you.
Thank you very
Johan?
much. Thank you very much for this presentation. You were also proposing to put your email address for anyone who has questions. Please feel free to do so in the chat for our participant. Thank you. Thank you everyone for joining this session. I will share with you the link to our feedback survey. If you have 3 minutes to fill it in, it's going to be really helpful for us. Thank you very much for your attention. Thank you to the speakers, and for those of us who are staying with us, we're having a 4-minute break, and we're meeting back at noon. Thank you very much.
Thanks all.